Okay, it's recording. Okay, take it away, Shannon.
Cool, thank you, Victor. Bye, everyone. Thank you for being here. It's all true. I'm Shannon. Yeah, I have really had some pretty disparate research interests throughout undergrad and grad school. So if you're also similarly trying to decide on a subfield to focus on, or if you're an early grad student worrying about finding a group, I'd love to talk to you and talk through some of those things. But today, the main thing that I'll be talking about is my research on antiferromagnets, and are they interesting but useless? So this phrase, interesting but useless, is commonly attributed to Louis Néel, who did a lot of the foundational work on antiferromagnets. It's commonly misattributed to his Nobel Prize speech. Actually, he said it somewhere else, first of all. Second of all, he said something slightly different. He said, they're extremely interesting from the theoretical standpoint, but do not appear to have any practical applications, which is a slightly nicer way to say it, but still basically the same thing. But yeah, so let's get into it. Let's see, are they really truly useless? But first, let's take a step back and let's say, what is an antiferromagnet even? Well, first, what's a magnet even? So when I say magnet, most people will think the kind of magnet that you can stick to your fridge, or like this bar magnet, you put the iron shavings around it, it forms these nice patterns. So what's going on in this case is that there's electrons inside of the magnet. They have spins, and those spins, which are basically tiny magnetic moments, want to point in the same direction as each other. And because of that, you have all of these tiny magnetic moments all working together, and you end up with this very dramatic effect, or these very dramatic effects that you can see on a macroscopic scale. And this is what's called ferromagnetism. So we have ferro being like iron. It's magnetic behavior, which is like what we see in iron. Okay, and something that I want to mention here is that as far as I'm aware, there are no ferromagnets that are always ferromagnets. So first of all, if you get it hot enough, it'll melt. But even before that, you'll actually stop seeing this behavior where all the spins are pointing in the same direction, and you start to get like the temperature winning. So below a certain temperature, we have all our spins pointing in the same direction. Above a certain temperature, they're sort of fluctuating, they're pointing in what seem to be random directions, although there's actually some information we can get about our material and what's going on microscopically, even from those random movements. Okay, so this is a phase transition between two different kinds of magnetism now. So we have, if we want to actually look at what that looks like, instead of just saying like this sticks to the fridge, now it doesn't, one thing that we can measure is what's called the magnetic susceptibility. So this is basically how easy it is to get these spins to align with a magnetic field. Another way to think of it, although it's slightly different, is that it's sort of you're adding up all of these spins. So they're all pointing in the same direction. They add up to each other instead of canceling out. And you end up getting below a certain temperature, this quantity erupts, and above a certain temperature, it's more or less zero. So down here, we have ferromagnetism. Up here, we have something else. And that something else is what's called paramagnetism. Okay, so we have two different kinds of magnetism now in our pockets: ferromagnetism, paramagnetism, where things are ordered and where they're not ordered. Now, what is antiferromagnetism? So let's zoom in and look at this magnet on a microscopic scale. So we have a bunch of atoms. They have spins which are pointing in certain directions. This is the ferromagnet, they're all pointing in the same direction. For an antiferromagnet, now each spin wants to point in the opposite direction to its neighbor. And so it'll look something like this, where if we pick out any single spin and we look at each of its neighbors, those neighbors are all pointing in an opposite direction. And this works out very nicely when we have a pattern like this, where atoms are forming a square lattice. When we go to different geometries, and also when we introduce different rules about who is and isn't a neighbor, things get a lot more complicated. But in this case, at least, things seem to be more or less manageable. Okay, so now we have it. We have an antiferromagnet. That's awesome. But now you might wonder, why are there antiferromagnets? because you can kind of think, right, if you have two like bar magnets and you put them next to each other, maybe you can convince yourself that they'll want to point in a certain direction with respect to each other. But what could possibly make it so that you have, in some cases, they want to point in the same direction, and in some cases, they want to point in opposite directions? Well, it turns out that inside of magnets, when we're talking about spins, it's actually a bit of a more complicated interaction that makes them want to point in the same or in opposite directions. And it comes down to a particular property of electrons. So if you have just an electron on an atom, if you have now two electrons on an atom and they're occupying the same orbital, one of those electrons will have its spin up and the other electron will have spin down. So you might have heard this before as the Pauli exclusion principle. Electrons want to be opposites to each other in some sense. So if spatially they're the same, spin is where they go to be opposite to each other. And another way to say that is that they're anti-symmetric. So if we swap them, we get the opposite scenario. But now what if we have two atoms? We have an electron on each atom, but they're still interacting with each other. And there still is like a sense in which they have some overlap in space. So now there are actually two ways we can go. One way would be to combine these so that I'm going to be a little bit big about this, then I'll go into a little bit of a more rigorous description for anyone who's taken quantum mechanics. But first, to give kind of like the sort of hand-wavy explanation. So there's one way that you can combine these spatially so that they're the same as each other. And in that case, you need their spins to be opposite. There's another way where you can combine them so that spatially they're opposite, and then their spins need to be the same so that on the whole, they are opposite. And so now if you're familiar with quantum mechanics, maybe a more natural way to think of this in a more rigorous way is that their joint wave functions have a spatial and a spin component. The spatial component can be symmetric or anti-symmetric when we exchange these electrons. And the spin component needs to be the opposite so that when we exchange them, there's an overall minus sign always. Okay. And so what I've just described is what's known as direct exchange. There are actually a whole bunch of different ways that like these ferromagnetic and antiferromagnetic interactions can come up. We can bring in another atom and have this kind of similar logic go through this like third atom. We can have even multiple atoms it's going through. We can sort of move through the conduction electrons that are carrying, like if we're applying a current, that's can be carried by the conduction electrons. But this is sort of the starting point for, I think, for understanding any of those mechanisms. And at the very least, I hope that I've convinced you that while it's not trivial to just say sometimes they point in the same direction, sometimes they point in opposite directions, it makes sense. And I hope you believe me.
So they're spin are opposite, they're in the same orbital. And I think just a quick, there's some binding in not in the same orbital.
Yeah, so they're still on separate atoms, but they, like the bonding is symmetric. Yeah. I guess maybe it doesn't make sense to think of them as being on separate atoms anymore, but there still are two atoms involved and the bonding is symmetric. Yeah. Okay, so I mentioned before that if we change this lattice to be in a different geometry, that things will get more complicated. So let's see what happens. So this, for example, is a triangular lattice. And if we try to play the same game we played before, so we're starting out with a spin pointing up right here. And we want now all of the nearest neighbors, so every atom connected by a line, we want them to have opposite spins. So let's say all of its neighbors now are pointing down. We've run into a problem because these two are also neighbors, same with any of these pairs, and they're pointing in the same direction. And actually, it doesn't matter if you flip any of these spins, the overall energy of this system is going to be the same. And it actually turns out that there are infinite degenerate ground states for this system. And if we just leave it here at this sort of very simplest treatment where we just have a triangular lattice, we have this preference to be anti-aligned with your neighbor, that's it. This should never order. We should always have our spins more or less pointing in random directions. But we know that we do order. So how do we do that? One way is to just take this one step beyond this sort of simplest, and that's what's called frustration, because the spins don't know what to do. They can't benefit energetically from all of their interactions. Okay, but so one way we can move beyond this is to introduce what are called thermal fluctuations. And all I mean by this is that we are now looking not just at what the energy of each of these states is, we're also looking at how the energy changes around those states. So we care about the fact that we're at a finite temperature. Our spins, however they are, they're always going to be moving at least a little bit around that orientation. And we're now looking at how that changes the energy. And that's breaking the degeneracy and making one state different from another state, even though their energy is exactly the same. Okay, and with that, we go from nothing happening to a set of ground states being chosen for this system. And this is a phase diagram. On the y-axis is an applied magnetic field. On the x-axis is a temperature. So as we move around with those parameters, we move into different states. Okay, and now there are other ways as well, but another one I'm going to point out is distortion. So to make this model a little bit more like a physical system, we can also distort the lattice a little bit, so that now, even though each spin still wants to point in the opposite direction to its neighbors, they care more about some neighbors than others. And that will give us another phase diagram, which is very complicated. I won't go into too much detail about this, not sure I could. But I just want the takeaway here to be that with frustrated antiferromagnets, things get very complicated very quickly. It isn't obvious what's going to happen and how the spins are going to orient themselves. And we also have a lot of states that have very similar energies to each other. So now we're moving from interesting to hopefully interesting and useful. Can we use this fact? Can we maybe move between these states, which in principle have very similar energies, in a way to get some low power applications? Okay, so people have used them, actually not taking advantage of what I just said, but here's a way that antiferromagnets are currently used and being developed for use. So this is a heterostructure, meaning it's a structure made of different materials. So on the top, there's a ferromagnet, there's a layer of a normal metal, which is not magnetic, there's another ferromagnet, and then there's an antiferromagnet. And so basically what this does, you're flowing a current through this, and you're able to change the resistance by changing the direction of the spins in this top ferromagnet, which is free. The resistance changes because it depends on the directions of the spins in that ferromagnet with respect to the directions of the spins in the other one. So if they're pointing in the same direction, the resistance will be lower. If they're pointing in opposite directions, it'll be higher. And whatever we're doing to move this top ferromagnet doesn't affect the bottom one because it's pinned in place by an antiferromagnet. So the property of an antiferromagnet that's being used here is the fact that it's really robust. It's really hard to get it to do anything. If we apply a magnetic field, you need to apply a really large one to actually get the spins to move around. Okay, and that's great. But if we were able to get rid of those ferromagnetic layers and just have an antiferromagnet and just be able to change the resistance of this antiferromagnet or otherwise store information in it, then at least in theory, we should be able to basically flip this bit faster and using less energy. And we should be able to store information more densely and in a way that's more robust, because like I mentioned, antiferromagnets, it's hard to mess them up. But those properties of the antiferromagnet, it's kind of like a double-edged sword, because at the same time, it's difficult to manipulate and it's also difficult to read. It's really, everything's sort of canceling out for a lot of typical measurements. It's hard to know exactly what's going on inside of this material. Okay, but we still want to. We want to change something about this material and its magnetism, and we want to be able to read that change. So what can we change? One option is called the nail vector. What is a nail vector? So close to the beginning of the talk, I showed you this plot of the magnetic susceptibility as a function of temperature for a ferromagnet. And it has this shape, right, where it's basically 0 when the spins are kind of random and chaotic, and it jumps up when the spins are ordered. So this is the shape of an order parameter. This is the ferromagnetic order parameter. More specifically, magnetization is the ferromagnetic order parameter, where we're basically, we're summing up all of the spins inside of the material. Now, what can we have for an antiferromagnet that will behave the same way? What can be the antiferromagnetic order parameter? That is the nail vector. So if now, instead of adding up all of our spins, we add up half of them, and then we subtract the other half, then we get something that's going to be finite and large when we have antiferromagnetic order, and it's going to go to 0 when we have a paramagnet. Because with a paramagnet, if you take half of them and you add them together, that's going to be 0. If you take the other half, add them together, that's still 0. 0 minus 0 is 0. So with the antiferromagnet, it works out very nicely. Okay. Yeah, so in the case of, oh yeah, the question was, how do you choose which ones to add and which ones to subtract? So commonly, you'll think of an antiferromagnet as having sublattices. So this applies in this sort of very special circumstance where we have everything pointing in one direction or the other. There are some more complicated orders where there's like, maybe like a third of them are pointing in each of like 3 directions, 120 degrees apart. But when you do have this kind of like nice order, which is called collinear, because they're all along the same line, then you're separating it out exactly by like the ones that are pointing up minus the ones that are pointing down. Yeah. Thank you. Okay. So here is the system that I've been working with, and where we've been storing information. This is iron intercalated niobium disulfide. All that really matters here is that it's a layered material with iron atoms sitting in between the layers. And all of the magnetism lives on the iron atoms. That's where all of the unpaired electrons are. And they form these really nice triangular lattices within each layer. Okay. And I do my measurements. I make devices using a focused ion beam. So this is a nice image that I took from the internet, so I gave some credit here. But basically, I'll be imaging my crystal using a scanning electron microscope. And at the same time, I'm shooting it with gallium ions, like a really focused beam of gallium ions, in order to cut very precise patterns into the crystal. And I'm also able to deposit specifically platinum. In principle, you can deposit a lot of things, but also with very high precision using this system. Okay, so here's an example of one of my devices. This is like the edges of my crystal. It's a sort of irregularly shaped thing. These little rectangles are where I've deposited platinum. Everything that looks white is gold. So basically the platinum is there to connect the gold on top of the crystal to the gold not on top of the crystal, so I can have a nice conductive path all the way out to where I'm connecting wires. These triangles are where I've cut away the crystal using the focused ion beam. And these lines are more cuts so that these conductive paths are separated from each other. And so that we have these really nice, like sharp, perpendicular, well-defined paths for the current to go through. And this is a smiley face because I thought it looked like a little bug. And I want to mention also that this flake is probably about half a micron thick. These bars are about 10 microns thick. And for scale, like a human hair is about 70 microns thick. So this is all very, very small. Okay, and so here's basically what we do in order to change the resistance, store information in this material. So we'll flow a small current in one direction. We're measuring the voltage between these two contacts. That gives us the plot on the right. Actually, it's resistance, but V is IR. We send a very brief current pulse in one direction, say this vertical direction. When that's done, we're in a high resistance state. We run a very brief current pulse in the horizontal direction. When that's done, we're in a low resistance state. So basically, we're sending these very short current pulses in order to change the resistance of our material. Okay. And so we know that this is connected to the magnetism in our material, because if we heat it up to where we're no longer an antiferromagnet, the behavior goes away. If we replace iron with other elements, then like structurally everything's very similar, but we see very different responses when we do this kind of experiment. But what we aren't able to say just from looking at this response and end of sentence is exactly what we're doing. So I will run through a couple other materials where people have studied this kind of behavior. There's been actually some more recent results which suggest that maybe the original interpretations of this data should be revisited, but I think it's still helpful to kind of walk through a little bit what they were thinking when they were doing very similar experiments. So they have a switching device like the one that I showed you, and what they thought was that they were changing the directions of their spins by 90 degrees. So this is exactly the nail vector rotating by 90 degrees within the plane of their crystal. There's also some consideration that has to do with the symmetry of their crystal, but that's not too important unless anyone's super interested in it. And this requires current densities on the order of 10 to the 7 amps per centimeter squared. Now in our system, again, very similar device. Our symmetry considerations are slightly different, although this should in principle still be possible just through a slightly different channel. But we've learned since doing these initial measurements through some other measurements that our spins are actually always pointing along the plane. Sorry, always pointing out of the plane. They're always pointing either up or down, so there's no room for there to be a 90-degree reorientation because they would never point 90 degrees away from the axis that they like. And I'll add as well that we require much lower current densities, although that's kind of a flex. Yeah, so yes.
I was just asking if you would expect the two different systems that it could happen. Like would there be evidence that this other different system could actually still happen?
So yes, kind of. Good question. So, sorry. The question was, is there a reason to think that there could be something else that allows 90-degree turns in our system? Is that correct?
Because they have a substrate right now material, so would that be different?
Okay, yeah. So why would this be different from what we would expect, given that it's a different material anyway? Yeah, that's a good question. I think I didn't. What I didn't touch on is that their measurements were based actually on this theory paper, which suggested like a very specific mechanism for why these things would be rotating, and they should be rotating by 90 degrees if we're to believe that that's what's going on. Yeah.
So
yeah, that's right. That's right. So we're seeing something definitely different from what they were seeing, and it seems to also be different from the theory that motivated them. Yeah, thank you. But so what is going on? So we're not rotating the nail vector. What are we changing? Okay, so it turns out there's a hint if we look at how the switching behavior changes as we change the amount of iron in our system. So if we start with our sort of perfect triangular lattice, and now we're taking away a few iron atoms, making it a bit more disordered, versus adding a few iron atoms and making it disordered in a different way. Then with the exact same setup, the exact same current pulse will bring our iron deficient samples to a low resistance state and our iron excess samples to a high resistance state. So we have basically completely opposite responses just by introducing disorder in two different ways. And something that I'll mention is that if we look at other measurements of our sort of perfect and then our two imperfect systems, there's basically no measurement that we at least do typically in our lab that has such a qualitative difference between these systems. So for example, this is heat capacity as a function of temperature. Basically these peaks are just showing that there's these very nice sharp phase transitions. If we go to an iron deficiency, the locations of those peaks move a little bit, although it's hard to see. If we have an iron excess, the locations of those peaks also move a little bit, although it's hard to see because the peaks themselves are really suppressed. And basically that's the story, is that the presence of disorder really muddies the picture, and it makes it hard to say with a high degree of precision even what's going on quantitatively between these systems, let alone like being able to pick out a qualitative change, like this very dramatic one that we're seeing in the switching response. Okay, so we have some collaborators who do neutron scattering studies. Neutrons are a really great way to study magnetic order because they have spin, but they don't have charge. And what they were able to see is that basically there are two different kinds of antiferromagnetic order in the system. So even though we have a triangular lattice, we know that the spins want to be opposite their neighbors. There's still a lot of room for what that can look like and what kind of patterns can come up. And it turns out we have one which sort of forms these little stripes. So here these dark circles are a spin pointing up, light circles are a spin pointing down, and another one which is a zigzag. So there are two kinds of order, two kinds of patterns, and each of these have three like orientations that they can take. The stripe can point in three different directions, the zigzag can point in three different directions. And it turns out that when we decrease the amount of iron just a little bit, the stripe will dominate. And when we increase the amount of iron just a little bit, the zigzag will dominate. While when we have our like really nice, perfect triangular lattice, they coexist. And so just to step a little bit into the weeds for a second, you might be wondering, how is it even possible at such a small difference? Because this is going from iron 0.31 niobium disulfide to iron 0.33 to iron 0.35. How can these tiny differences lead to a total change in what even the preferred order is? It turns out that it comes down to some really fine details of our the strength of the preferences to anti-align with your neighbors. So, right, so, sorry. So I've shown you that the spins are gonna want to point in the opposite direction to their neighbors. But there are many degrees of that. So there's your first nearest neighbor, then there's your second nearest neighbor, which will have a different strength of that preference. There's your first nearest neighbor in the next plane. There's your second nearest neighbor in the next plane. There's your third nearest neighbor, etc. And so it turns out it comes down to these three like really distant relationships and how exactly they compare to each other. So that's what's changing very slightly when we change the amount of iron and leading to this really dramatic like qualitative difference in what the magnetism is doing. Right, so in one case the stripe wins and in the other case the zigzag wins. So now we have a pretty good idea of what's going on microscopically when we're switching our material. So it's not the Néel vector that's reorienting, but it's actually the directions of these domains. So that's why when we have the same pulse bringing our iron deficient sample to a high resistance state and our iron excess sample to a low resistance state, it's because we're preferring these two orientations of domains, but they're sort of fundamentally different domains to start off with. They're different kinds of order. Okay, yes. Oh yeah. So each of these dots is an iron atom. I'm showing just a single plane of iron atoms. And then the lines are connecting spins that point in the same direction as each other. Yeah, that's exactly right. Thank you. Yeah.
How do you know which domains correspond to plane?
Yeah, so we've been working on getting some like real microscopic during the scanning measurements to get that for sure. At this point, we know from DFT calculations. Yeah. Yes.
How do you know how to reach?
Oh yeah. So our kind of there's yeah. How do we know how pure our sample is, or how like what the amount of iron is? Yeah. So there are three lines of defense we have for this question. Basically, first, there's a really precise measurement, which is ICP, or inductively coupled plasma, And that gives, like, if we give a bunch of crystals and they all get destroyed, it's able to tell us exactly what the ratios were. Another one is EDX, or energy dispersive X-ray spectroscopy. This one is nice because it doesn't destroy your crystal and you don't need a lot of it, but it's a little bit less precise. Another one is that if we look at the magnetization of a crystal, we can tell from like sort of the shape of it and also exactly where the transition temperature is. We can at least tell like how far we are from perfect, although we need those other measurements to know like if we're over or under. Yeah, and then we also do rely a bit on the fact that so when we grow these crystals, we grow them in like a whole batch. Generally, for these samples, we found that within a batch, they're pretty homogeneous. So that's very thankful, because then we're able to, you know, destroy half of them and then be fairly confident that we know what's going on in the other half still. Yeah, thank you. Okay. Yes. So now we know, or at least we have a pretty good idea, when we are applying these current pulses, how does the system look different after the pulse has been applied, and why are we able to read out these resistance changes? The question remains, how are we able to prefer these domain orientations? And that's still a bit of an open question. But as we're trying to answer it, one thing that we've been looking at is magnetoelastic coupling. So here, basically, the idea is that it's kind of like when I was showing the distortion affecting the magnetism. If you distort your crystal, that's also going to affect the magnetism. Likewise, going the other way, although I think it's slightly harder to imagine, if you get a certain magnetic order, you'll also sometimes distort your crystal if there's that coupling between the magnetic and the magnetic and structural degrees of freedom. And so we have some collaborators who had done some work before showing that if they apply strain on these samples, so they're like squeezing them or they're pulling them, that they can prefer certain orientations of these domains. So this is really pointing to there being magnetoelastic coupling in these samples. Okay. So in order to look more at this and how it might affect the measurements that we're taking in these switching experiments, we put switching devices onto a cube of piezoelectric material. So a piezoelectric, if you apply a voltage, it's going to deform. So basically, in this diagram, 1 and 2 are electrodes, 3 is the cube, and this arrow is the direction that the cube is going to expand when we apply a voltage between those electrodes. We put the device on the side. Here's an SEM image of the device. These like hemispheres are where the leads are soldered onto the electrodes. This like blob is actually some glue that transfers strain pretty well. And then the device itself is like completely covered by the laser pointer when I do that. Okay. And so here's what we saw. So first, a baseline measurement. This is iron excess. We have high-low switching. Iron deficiency, we have low-high switching. And now this device is actually one that was on the piezo when we cooled it down under strain. And this is how the switching changed. So before we had low-high, now we have high-low. And this is really surprising. So yeah, at least naively, I was expecting that if we have these certain domain orientations, they're connected to the structure, we cool it down while squeezing it, we're sort of freezing things into place. You know, maybe we'll have a lower amplitude because we have fewer domains that we're able to manipulate. Instead, we see this sign flip. And the story actually gets even more complicated when you look at how this behavior evolves as you change the amount of current that you're putting through and everything. But for the time being, the sort of takeaway here is just that there's definitely strong magnetoelastic coupling in this material. It affects the switching in really non-trivial ways. And I think can be a really important key moving forward in sussing out the details of what exactly we're doing. Okay, so antiferromagnets, they seem to be pretty useful while also being pretty interesting. So I wanted to also bring it back a little bit to what Neil actually said in his Nobel Prize speech. And he told this story about how he had been doing a bunch of work on magnetism and then went back into, I don't know, the library probably at that point, and found that a bunch of the work he had done had actually already been done 100 years earlier by someone who was trying to make better compasses. And so, I liked this quote from his speech, that the much talked about university industry link today is actually very old. And I think this really speaks to the fact that fundamental and applied physics always have fed into each other and always have inspired each other. And I think both are much richer for it. Okay. Thank you very much. Oh yeah, so we do what's called chemical vapor transport. So we start off with all of our elements, just like as powders. We mix them in like the proper ratios. We like seal them into these glass tubes using a blowtorch. Actually, I skipped a step. We put in a little bit of iodine too. We put it into a furnace so that there's a temperature gradient, and then the iodine picks things up and drops them off, and then it sort of forms into a crystal on the other end.
And there's only one way crystal these three elements.
Yeah, more or less. So there's if you decrease the amount of iron so that the ratio is 1 to 4 instead of 1 to 3, there's a different structure that forms. And if you don't have iron at all, there are multiple structures that just niobium disulfide can form. Yeah. Yeah.
You said that you have hunches as to which domains correspond to what this DFT. Does the DFT reveal what the physical mechanism is for the resistance being different? For the different domains?
Yes. So let me get out of this. I should keep sharing my screen though. But not that one. Oh no. Here we go. Now you can see all my hidden slides. All the secrets I didn't share with you. Yeah, so they've shown that the Fermi surface becomes anisotropic when we have these domains, and that the anisotropy is sort of opposite for the stripe and for the zigzag. Yeah. These are cool looking plots, but I don't know enough to confidently just put it up in the main part of the talk. So
in your sample, you have the distinct color finding. Oh, you said they're all.
that's right. Yeah, I think that with the off stoichiometry, like the disordered samples, maybe there's a little bit more room for there to be some canting within the plane. At least from looking at like some other measurements that we've done, but not all that much. So that's actually something we were looking at for a while. We just saw that like we introduced disorder, now we get the switching, we have the perfect sample, the switching is basically gone. We thought for that reason that still this in-plane component was really important. But now we know that even with the disorder, it's still pretty small.
Any other questions? If not, let's thank our speaker one more time. Fantastic. And